Okay, what we're talking about now in class is the idea of a function composition. That's when a function, rather than just acting on a single numeric value, a function is going to be acting on an entire function. So for example, we talked about how you could have an input value of x go in, and to some function, we'll call it g for the sake of this picture, and g, it could be a simple function like x minus 5, it could be a quadratic, it could be a sinusoid, it could be any of the functions we've talked about. But that entire function then acts as the input for another function. So f of g of x would mean that the function f is acting on this function g of x. And believe it or not, you've already seen this in action a whole bunch of times already in your math career, just you haven't really worked at the process of kind of creating a function this way, or what we're going to work on later is decomposing a function this way. In other words, seeing a function that is a result of a composition of two functions and then kind of breaking it down to see which one is acting on what. So our first example here, example 3, that employs this is you got a quadratic f of x is x squared plus 3x plus 4, and g of x is 5x minus 1, and we're being asked to find f of g of x and g of f of x. It's really important to understand that these are two different ideas. One is g of x, the function is getting acted on by f, and in the other function, f of x is getting acted on by g. So you kind of always sort of start from the inside function, follow what happens to x. So x is in here on the inside. Next thing that happens is g acts on it, does what it's going to do to the value, and then f acts on that result. Okay, so what we're being asked to do is find f of g of x, and so I've got our functions that we can refer to up here. F of x is this quadratic, and g of x is this linear function. And first we're going to look at f of g of x. And again, in class, I kind of mentioned it would not be a problem for any of us to consider, say, what f of 5 would be. F of 5, you'd plug a 5 in here and square it, and add 3 times 5 and add 4 to that, and get your numeric value. Well, now what we're doing is we're going to take g of x, this entire function, 5x minus 1, and it's going to go in and it's going to get squared, and it's going to get multiplied by 3, and we're going to add 4 to it. So I kind of showed g of x in blue here, so I'll kind of continue that theme. Because the x shows up in two places. It gets squared and then it gets added or multiplied by 3, and that result is added to the square. Then we add 4 to it. So I'm going to think of that 5x minus 1 getting squared, and then we're going to take 3 times 5x minus 1, and then we're going to add 4 to it. So you can sort of see physically that we've just substituted 5x minus 1 for each of these x's in the original function. Now, of course, we can go ahead and simplify this just by foiling out the binomial expansion and distributing the 3 and grouping our like terms. So this is going to be 25x squared minus 10x plus 1 plus 15x minus 3 plus 4, and we group our like terms. 25x squareds, we've got minus 10x and plus 5x is plus 15x is plus 5x, and a 1 and a 4 is 5, minus 3 is 2. And so we could say, all right, here's f of g of x in simplified form. Now, the thing to remember is this just looks like a quadratic that we've seen 100 times, but we have to remember that this quadratic was born of this linear function working inside of this quadratic function. Now, in this case, it's unremarkable because the domain of all these things, of a linear function and a quadratic, is all real numbers. So we're not going to have any issues, but we may see in later examples that if either one of these guys, either one of these functions, f or g, had some domain issues where they didn't let certain values of x in, we would have to be concerned about that and continue that domain restriction, even though the resulting function looks like it would take in all real numbers. Now, we were asked to identify the domain of this new resulting function f of g of x, and our domain would simply be all real numbers. Again, for the reason I just addressed, that the inside function of g of x, his domain is all real numbers, his output is all real numbers, and therefore we're not going to have any issues there. And then the result of that is, like we said, the result of g of x is just going to be all real numbers in its range, and those values get plugged in here. 5x minus 1s get plugged in here and here, and there's not going to be any issues with that. So it's really a simple problem when both functions have domains of all real numbers. And so we're going to see that again when we look at g of f of x. So if we want to kind of construct g of f of x, we'll say g is going to act on f of x. I'll make f of x stand out in red this time. And so that means that wherever we see an x in g, we are going to be using f of x. So f of x is x squared plus 3x plus 4. And that's going to be acted on by g, which takes things and multiplies them by 5 and then subtracts 1. So all we need to do to simplify this guy is distribute the 5 plus 20 minus 1, and we get 5x squared plus 15x plus 19. And that's g of f of x. And again, for the same reason as before, the domain of this guy is just going to be all real numbers. Okay, so I've got our next example ready to go here, and we're being asked to do another composition. We've got f as a rational function, 2 over x plus 5. G is a linear, 5x minus 10, and we need to do, again, f of g and g of f and find out what the domains are for each. So now that we have a rational function involved, we know enough to realize that rationals are where we have to concern ourselves with the potential of dividing by 0. For example, the domain of f would be needing to exclude any x values that are going to make the denominator 0, namely x equals negative 5. So the domain for f would be everything except, all real numbers except negative 5. Now that we're going to be inputting 5x minus 5x minus 10 into this function, we'll need to take a look and see what our domain is. So what I've done here is kind of set up a template for f of g of x. I've got f ready to go here, which is 2 divided by whatever's inside the parentheses plus 5. Just what's in the parentheses now is g of x, so I'm going to put g of x in there. I could put parentheses around it just to kind of make a point, although mathematically those parentheses aren't really doing much because it's just 5x minus 10 plus 5. The reason I'm going to do this, though, is because this is a great way to get a check on what your domain for this new composition function is going to be. So for example, we always want to look at the inside function and see what his domain is. Well, 5x minus 10, the domain is all real. So initially, we're thinking we're not going to be problems here. However, as soon as we drop this guy into the denominator, we're going to realize that potentially we're going to have an issue with what it would take to make the denominator 0. And this is the best time to check that. After you've created the function composition, f acting on g of x, but you haven't simplified it yet. And we'll see what I mean by that maybe in example 5. But for right now, we just have to realize that as far as our domain goes, we're going to concern ourselves with this expression right here and what it would take to make the denominator 0. For now, though, we can go ahead and simplify this, and the denominator is just going to become 5x minus 5, and there's our simplified result. So as far as the domain goes for this guy, we can just look either here or there and say, okay, what's it going to take for that denominator to be 0? So 5x minus 5 is equal to 0 when 5x equals 5, or therefore when x equals 1. So those are values, that's the value of x that we would not be allowed to have. So our domain will be all reals except 1. So we'll just write it out in interval notation, and we're good to go. All right, so now we're going to create g of f of x, and we've got our function template kind of ready to go. G is our outer function, so it's going to take what's in its parentheses, multiply it by 5, and subtract 10. Now the issue, though, is the function that's going to be working on is this rational function 2 over x plus 5. And again, this is a good time to take a look at our function to decide if we're going to have any domain issues. This is the composition G was working on f. So if there's any issues right now, before we go and simplify this thing with what would create a 0 in a denominator, we need to respect it right now. So again, it looks like the denominator of x values equaling negative 5 would be the problem here. So we're going to go ahead later on and identify that as an issue. But if we want to simplify this thing, all we got to do is distribute the 5 in here. 5 times 2 is 10 over x plus 5 minus 10. That more or less is simplified. It's got a no parentheses left. If we wanted to, though, to clean this up a little bit more, we're going to work on this when we get to rational functions, how to add and subtract rational functions. Before we can ever add or subtract fractional terms, we need to make sure we have a common denominator. So if we think of this denominator over here being 1 and needing to have the denominators be the same, we could give this guy an x plus 5 over x plus 5. And therefore, now we have a common denominator between our two fractions of x plus 5, and we haven't altered the value of this fraction right here because all we did was multiply it by 1. Anything over itself is equal to 1. So if we clean up this fraction on the right, let's see, that's going to be negative, let's get rid of that equal sign, minus 10x minus 50 over x plus 5, and then we have 10 over x plus 5. We can now go ahead and group those numerators. So we've got 10 plus 10x minus 10x minus 50, a little negative sign in there, over x plus 5. So you can see I got a little sloppy with my writing here. I was distributing this negative 10 into the x and the 5 and got negative 10x minus 50. Therefore, that's why this minus turned into a plus, because I'd already distributed the negative. So let's group our like terms. 10 minus 50 is negative 40. So we'd have a negative 10x and a minus 40 all over x plus 5. And again, it doesn't really matter right now whether we look at this simplified version or this version way up here before we ever did anything. It's pretty clear that x can't be negative 5. But again, we really want to focus right here because sometimes in the simplification process, the issue might, what might be a domain issue might kind of get hidden in the simplification. Might look like it's gone away, but it's not. If this is g of f of x here, we have to respect the domain that we get before it's simplified. So we're just going to state that the domain is all real numbers except for negative 5. A little sloppy there, but there we go. All right, so here in example 5, we're going to see a case where this domain issue is going to kind of pop up, and one of the things I was cautioning about in the previous two examples. So f of x is this quadratic x squared minus 9, and g of x is just root of x. So g of x clearly has a domain issue because we can't take the square root of negatives. So the domain of g would be x values that are greater than or equal to 0. And because for this first part, where we're looking at f of g of x, he's the first guy that is working on x. So in other words, if we think about that idea of x walking into a function and getting operated on and then coming out the door and then getting operated on by a second function, that first function, if there's any domain issues there, we're going to make sure that x can't be that value, or any values that are restricted by that first function. So even though when we plug g of x into this and we put root of x in there, so in other words, that root of x is jumping right in here and getting squared right away, you might say, well, when we square that root of x, it's going to not be a problem, it's just going to become x. And our simplified version might look like this, x minus 9. And if you're just looking at that function, you'd say, oh my goodness, that's just a linear function. So that domain is all reals. However, it's not just x minus 9. That function was born of the square root of x existing. So therefore, x's can't be negative numbers, so we're going to just talk about x's being 0 to positive infinity, and then getting squared and then subtracting 9. Because this domain is the domain that goes with this inside function, we've got to respect that, and that's the domain for our composition of functions. Now, we're going to look at g of f of x, and in this case, g is working on f, and you might say, okay, well, this isn't going to be a thing because the inside function now is f, and g is just going to square that. So we have to think about x squared minus 9 now getting square rooted. Well, this is where we want to kind of take a lesson from earlier in the day where I said once you have the function expressed, you now need to take a close look at it and make sure that there's nothing that could go wrong. And when we say, well, if x squared minus 9 turns out to be something negative, we're certainly going to have a problem. The other thing that's real important here is to realize that a lot of students, when they see an expression like this with a square root of a sum or a difference down here where there's adding or subtracting going on, they think, oh, let's just take the square root of this guy and the square root of this guy, and they'll write an expression something like x minus 3. And that is really wrong. You can't apply a power or a square root to a sum or a difference just by taking the power of the square root of those individual terms. So that's one way to really upset your teacher, is to apply a rule like that that's actually not a rule. So this is as much as this is going to simplify, but our domain issue becomes a little bit of a thing, because we have to think about what values of x would make x squared minus 9 negative. So probably the easiest way to think about this is imagine x squared minus 9, which is a quadratic, so it's going to have a parabola as a graph. And I think everybody would recognize the intercepts are going to be at 3 and negative 3. And so what we want to do is avoid all these values down here where the y values are negative, which means we can't let x be these numbers inside here between negative 3 and 3. So we're going to have a domain that's going to be all real numbers except the numbers between negative 3 and 3. So it's going to be negative infinity to negative 3 in union with 3 to positive infinity. Now, I intentionally left the parentheses brackets issue off because I want to think about can x be negative 3 and can x be positive 3? And I think all you have to do is realize that, hey, if x was negative 3 and we square it, we get 9 minus 9 is 0. And then you just ask yourself, is it okay to take the square root of 0? And of course it is. That's not going to be an issue, so we can use a hard bracket on both of these guys. All right, so there we go. There's a few examples of function composition with, some of the ones that we would expect might cause some issues. Radical and a rational function in particular. Those are the ones where we've got to watch the domains. So we will pick this up in class again next time, but I wanted to have you guys get a chance to look at some of these and get a sense of how they work, especially maybe with the colors helping out a little bit.